Hi, we will wait for a few more minutes, then we will start the session. Can someone confirm if I'm audible?
Yeah.
Okay. My slides are visible, right?
Yes.
So let's wait for 1 more minute, then we can start. Okay, I think we can start. So, hello everyone. My name is Arpit Bal, and I'm a PhD scholar from Department of Electrical Engineering, IIT Bombay, and I'm one of the TA for this course, Digital Circuits. In this particular live session 11. So, what we are going to do is few problems related to 8085 microprocessor. So in the previous live sessions, we covered basics of digital electronics, starting from the number system, floating point representation, logic gates, combinational circuits, sequential circuits, memories. So in today's session, we will be covering more on problems related to 8085 microprocessor. Okay. So with this brief introduction, let us start today's session. Okay. So the first question is related to something called as T states that are required to execute an instruction move A comma C. Okay. So T states are actually they refer to the number of clock pulses of a microprocessor. Okay. So they are measured in terms of, so any instruction that is being executed, so we do not directly say that it is going to take, let's say, 1 microsecond. We refer it in terms of T states. Okay. Then based on the frequency, we determine what is going to be the absolute delay that is associated with each T state. So what this question is asking is, so for this particular instruction move A comma C, how many such T states are required? Okay. So does anyone know the answer? For move A comma C?
4.
Correct. So for move instruction, the number of T states required is 4. So okay, one T state is equal to 1 by frequency of operation of microprocessor. Okay. So 4 T state will be equal to 4 into 1 by frequency of operation of microprocessor. So using these relations, we can figure out how much exact time this particular instruction is going to take, given that we know the frequency of operation of the microprocessor. So for move instruction, it is 4. Now let me mention some common instructions and their respective T states. Okay. So MVI instruction will take 7 T state. Move instruction will take 4. Jump not. Okay. JNZ instruction will take 10 T states. Okay, during execution. Okay, so JNZ is basically used for looping, right? So if we want to perform an action repeatedly, then we use loops. So if you are familiar with C, so this will be something like a for loop or a while loop. Okay. So when it is looping, it will take 10 T states, but in the terminal loop, the last iteration, what will happen is it will take 7 T states. Okay. Similarly for ORA, it is 4 T states. For LXI, it is 10 T states. For DCR, it is 4 T states. So these are some common instruction with their respective T states that are needed to execute these instructions, and these things we will use in the subsequent questions to solve the numericals whatever is present. Okay, moving to the next question. So the next question asks us what happens to the content of the stack pointer after push instruction is executed. Okay, so before attempting this question, let me tell you a few points related to the push instruction. So in the microprocessor we have certain amount of memory available. So that memory is called as a stack. Okay, and it is available for the programmer's use. So it can be used for temporary storage of information, and these two instructions, push and pop, they are related to that operation of stack. Okay, and there are few points that you will need to keep in mind. That stack grows backwards into the memory. Okay, push refers to storing info on stack, and pop refers to retrieving it back. Okay, another thing, LIFO. So stack, the operation in stack, it is associated with something called as LIFO. It means last in, first out. Okay, so let me give an example. What happens when, let's say, I write an instruction called as push B. The first thing that is going to happen is, so as it is mentioned that stack grows backwards. Okay, so the first thing that will happen is the stack pointer. So stack pointer is a pointer that keeps track of the location of the memory, okay, where the stack is going to be present. So when I write push B, what happens is the stack pointer is decremented. Okay, then copy the contents of register B to the memory location pointed by stack pointer. Okay, so push B means I am trying to push something into the stack. Okay, so whatever is present in the register B, I am trying to push it into the stack location. Okay, next, after that, what happens? Copy the content of register C. Okay, so after this operation, then stack pointer will decrement again. Okay, then copy the content of register C to memory location pointed by stack pointer. Okay, so basically BC, there are few register which can be used in pairs, like BC is one of them. So when I do push B, so it means that I want to push the contents of BC register into the stack. Okay, so the first step that is going to happen is I will decrement the stack pointer, not I. So the operation is such that the stack pointer is decremented. Okay, then whatever content is present in register B, that is copied into the location that is pointed by the stack pointer. Okay, then the stack pointer is decremented again, and whatever content is present in register C, it is copied into the location pointed by the stack pointer. Okay, so in this process, how many times is the stack pointer decremented?
2 times.
Correct. So what happens to the content of the stack pointer after push instruction? So the stack pointer is actually decremented by 2. Okay. I hope this part is clear. So you need to remember these few points. Okay, that stack grows backwards, last in first out, that's the property of stack. Then push and pop are the operation. Push is for storing, pop is for retrieving the information back. So just like we did for push, that the stack pointer was being decremented, in case of pop the stack pointer is going to be incremented. Okay, so similar analogy you can solve problems. Another question which, if it is related to pop instruction, you can solve it. Okay, moving on to the next question. Okay, so in 8085, which of the following instruction update the program counter? Okay, so basically program counter is a register that holds the address of the next instruction that needs to be executed. Okay, and what this question is asking is, we need to figure out, so which of these instruction is going to update the program counter?
All the instructions.
Correct, it is actually all the instructions. Okay, so I guess PCHL was probably not covered in the lecture, but it loads the content of H and L into the program counter. Okay, so and add instruction will obviously be there, because so anytime you execute an add instruction, so the next instruction needs to be fetched, so program counter will anyways be updated. Okay, so moving on to the next question. So next question is related to something called as chip select signal. Okay, so what is chip select? So if there are a number of memory chips that are available to you, okay, let me call it okay, let me give it number, like number 1, number 2, number 3, okay, so on and so forth. Then if I have to select okay, if I have to select any one of the memory, so what usually happens is there is an enable signal associated with each memory. Yeah, there's an enable signal associated with each memory. That enable is called as a chip select. Okay, so if let's say the chip select signal is of 2 bit, so if I do 0 0, okay, let me give it number 0 1 2. If I do 0 0, then 0 will be selected. If I give 0 1, 1 will be selected. 1 0, number 2 will be selected. Okay, so that is basically the chip select. And in this case, what is told is the chip select is equal to A15, A14, A13 bar. Okay, so there is a tick. Okay, so that refers to complement. So it means that whenever CS is equal to 1, okay, then this memory will be enabled. So can anyone tell me, so what should be this value so that CS is 1?
For A15 110.
Correct.
Because as it is.
Yeah. So if A15, A14 and A13 bar is 110, then this chip select will be enabled. Okay. So we know that the address bits are of 16 bit. Yeah, Suresh. Okay, I saw someone raising hand. Okay, yeah, so address bit is of 16 bits width. Okay, so we will have A15 to A0. fine. But out of that, only this particular combination is going to select my chip. So let me write it like this. So this has to be 110. Okay, rest anything can occupy any position. Okay, so let me group them into bits of 4. So A15, A14, A13, A12. Okay, then similarly A11 so on, then like this, then at the end I will have A0. So if I have 110X, okay, rest everything is grouped into 4 bits. Okay, so can anyone tell me what is the lowest value that we can get out of these combination?
It is C 000, I think.
Yeah, it is C000. So we are going to represent it in terms of hexadecimal. We have grouped it in bits of 4. So the lowest will be when this part is 0, right? So we have 1100 and rest everything is 0. Okay, so what can be the highest if I assume that this is fixed 1100? What can be the highest value that the rest of the things can occupy?
CFFF.
Correct. Okay, similarly, let's say this X is equal to 1 now. So in that case, what will be the lower order bits?
It is D000.
Correct. Similarly, it will go till D FFF. Okay, so the important point to note here is, so which bits are going to get fixed, right? Because these bits are going to be used as a chip select signal, so these bits are not going to change. Okay, so the rest of the things are actually straightforward because this can occupy any value. So basically we have C000 to DFFF. That's the memory range that is available to us. So option C is the correct answer. Okay. Okay, so moving on to the next question. So the next question is related to the contents of accumulator. So there is one operation that is being performed here, and we need to figure out what is going to be the content of A as well as the status of carry and sign flag. Okay, so the microprocessor has some status flags available to let you know that when there is a carry, when the accumulator is 0, when what is the sign flag and those things. So those are used to perform a number of functions like the jump on 0 instruction, right? So how will it know that this accumulator is 0, right? So when the 0 flag is set. Similarly, let's say there can be another operation that based on whatever is the sign. If it is negative, then add +2. Okay, so how will you know that a number is negative or not? So sign flag in that case can be used. Okay, so what is given to us is the content of register B is 49H, content of accumulator, let me denote it as A, is 3AH. So H indicates for hexadecimal number, and this is the content 49 and 3H, sorry 3A. Okay, so what is the operation? The contents of A after executing sub B instruction. So sub B instruction means subtract the content of B from the accumulator. Okay, so let me write 3A in terms of binary. So it will be 0 0 1 1 and A is 1 0 1 0. Okay, then let me write B. 4 will be 0 1 0 0 and 9 is this is 8 0 0 1. Okay, so we will have 1 0 0 0 1 1. Here we will get a carry, so there will be another one. Okay, and there will be a carry out. Fine. So because there is a carry out, along with that the result is actually a negative number. Yeah, the result is actually a negative number. So this carry that is going out, it sets the carry flag is equal to 1. Because the result is a negative number, so sign flag is equal to 1. Okay, and what is the content? It is
F1.
Correct, it is F1. Okay, so option A is correct. Does anyone have any doubt in this question? Okay, then we can move to the next question. Okay, so this question is related to calculating the time required to execute the time required to execute an instruction is given to us. We need to figure out the number of T states. Okay, and the clock frequency of microprocessor is given as 5 megahertz to us. Okay, so similar to question number 1. Okay, but in this case we need to figure out what is the number of T states. Okay, okay, so total time taken is equal to number of T states into 1 by f clock, or the frequency of operation. So using this formula, can someone calculate what is the number of T states needed for executing this instruction? It is already given what is the total time taken, that is 1.6 microsecond. F clock is given as 5 megahertz. Okay, mega is 5 into 10 power 6. Okay, so from this, can anyone calculate what is number of T states?
Eight.
Yeah, 8 is the correct answer. Okay, this implies number of T states will be equal to 1.6 into 10 to the power minus 6 into 10 to the power 6 into 5. Okay, so we will have 8 T states. Okay, so is everyone clear, or is there anyone who has a doubt in this question? Okay, so moving on to the next question. Okay, so we are given a set of 5 instructions, and we need to figure out at the end of execution of all these 5 instructions what is the content of accumulator. Okay, so MVI A comma 65, what it does is move 65H into A, okay, accumulator. MVI B comma 12H means move 12H into B. Add B means accumulator is equal to B plus the content of accumulator. Okay, CMA refers to complement the content of accumulator. ANI refers to and immediate 68H. It means and between A and
08.
68H. Okay, yeah, let us see whether we arrive at that. So after first operation, A will have content 65H. After the second operation, the content of A will remain same. B will have 12H. After the third instruction, we will have 65H plus 12H in the accumulator, that is equals to 77H. Okay, so 77H, let me write it in binary. Okay, so now in the fourth instruction, the content of A is going to be complemented, so it will be 1 0 0 0 1 0 0 0. Okay, at the fifth instruction we are going to AND this content with 68. So 68 is 0 1 1 0 and 8 is 1 0 0 0. We have to AND these two, so it will be 0 0 0 0 and 1 0 0 0. So 08 is the content of accumulator. Okay, is this question clear? So this is actually an important question because many a times it is asked to figure out what is going to be the content of accumulator after the execution of these following instructions. Okay, so I'll wait for 1 minute here so that you can give it a look and let me know if you are stuck anywhere in this explanation for question number 7. Is question number 7 clear?
So,
Okay. Okay, then we can move to question number 8. Okay, so here we are given the delay produced by each instruction, and we have to figure out what is the total delay that is going to be produced by the given program. So in this type of question, first thing that you should note is if there is a loop. Okay, so step 1 is ask this question: is there a loop? If no, then add up all the delays. If yes, then figure out how many times the loop will be executed. Okay, so let us go step by step. So first thing is there a loop? Yes, there is a loop. Okay, so now how many times is this loop going to be executed? Okay, so let us see what is the condition of this loop. So the condition is DCXB. Okay, that B is going to be decremented, and okay, so the condition is JNZ loop. So jump not 0. So this loop will be executed until B goes to 0. Okay, and how does B change? So B is basically decrementing in this loop. Okay, so first thing that you need to make note of is what is the value of B. Okay, so B has the value So actually BC has the value 0123H. And what does 0123H stand for in decimal? 0 plus 16 square plus 2 into 16 plus 3. Can anyone tell me the value? Yeah. So this loop is going to be executed for 291 times. Okay. Then T delay is equal to TO plus TL, where O is the delay outside the loop, TL is the delay inside the loop. Okay. So TO is visible that it is 10T to load the value into B. Right? But now we need to figure out what is TL. Okay. TL is equal to total delay in the loop. That will be equal to individual loop delay into number of times it is executed. Okay. But there is a catch here. Okay. So what happens is JNZ instruction takes 10T states for each time it is executed, but in the last execution what it does is it executes for 70 states. It takes that much time. Okay, so what we can do is to compensate for that error, let us write it as minus 3T at the end. Okay, to account for the terminal loop. Okay, so what will be the total number of T states for TL? It is going to be 291. That is the number of times this loop is going to be executed into the individual loop delay. So 6T plus 4T plus 4T plus 10T. So we'll have 6 plus 4 plus 4 plus 10. Okay, and minus 3. So what is this value inside the
minus 3.
Yeah, it is 24 minus 3. That is equals to 6981 T states. Okay, here we have obtained the answer in terms of T states. Okay, so this is for TL. So let us find out what is T delay is equal to T naught plus TL, and T naught is equal to 10T plus TL is equal to 6981T. That is 6991T. Okay, and we are given that it operates with a 5 megahertz clock. Okay, so it means T delay in terms of actual value is equal to 6991 divided by f clock, that is 5 megahertz. 5 into 10 to the power 6. So can someone calculate and tell me what is the answer?
Option A 1.398.
Okay. Option A 1.398 millisecond. Yeah, option A is actually correct. Yeah, it is visible from here itself, like if you see the unit, so it is, so you can write 6991 by 5 microsecond, but this is going to be approximately yeah, this is greater, so you can write it as 6.991 by 5 millisecond, and the first number is going to be anyways 1, so 1 point something x millisecond. So with that observation itself, we could have told that it is option A, because other units are microseconds. Okay, so yeah, correct, 1.398 milli. So that is the correct answer, option A. So does anyone have any doubt in this question, how we solved this? So this is a good question when it comes to loop. So if you are clear with how we solved this question, then I don't think the normal question related to delay calculation will be an issue at the later stage. So is it clear for everyone, or does anyone have any doubt?
We explained that -3 is that
Okay.
-3. Why?
Yeah, so this -3 was done to account for this JNZ loops delay. So here JNZ loop is written as written that it is taking 10 t states. Okay, but 10 t states is when it is executing. Okay, for the last state, it actually takes, for the last execution, let's say a loop is being executed for 0, 1, 2, 3. Okay, so for the first execution JNZ will take 10t, for second execution it will take 10t, third execution it will take 10t, but for the last execution it will take 7t. Okay, but in this case, for this calculation, what we have done is we have assumed 10t for each and every case, right? To take care of that particular condition, what we have done is we have subtracted -3, okay, to take care of the last state.
Okay.
Okay. Yeah. Is there any other doubt? So is everyone clear with this question, or is there a doubt that needs to be addressed? Okay, so we can move to the next question. Okay, so in this type of question, the first thing that you should identify is if there is a loop, because what I have noticed is, so many people, when such a question is given, if you don't notice the loop, then probably you will say it will be addition of all this, right? So that is going to be wrong. So that is the number one thing that you should observe if there is a loop. Okay, second thing is, don't forget to take into account that the terminal state of J and Z, it actually takes 70 states, not 10t. Okay, so these two are the points that you should keep in mind while solving such a question. Okay, let's move on to the next question then. Okay, so the next question is related to the addressing mode that is used in this particular instruction, LDAXB. Okay, so can anyone tell? Okay, so in 8085 we have something called as, yeah, option C is correct, that it is indirect addressing mode. Okay, and why is it called as indirect addressing mode? Can anyone tell me? So when it is said that it is LDAXB, what does it mean?
It means the address which is stored in BC pair, the content of that address will be loaded to accumulator.
Correct, the content of that address. So because the content of that address, instead of directly mentioning the memory here, okay, the content that is present in the address indicated by BC pair, so that is going to be loaded. So that's why there is an indirect approach. So that is why it is in indirect addressing mode. Okay, had it been LDA 4000 or something, that's a direct address mode, because so 4000 is directly going to get added into this, is going to get loaded. So moving to the next question. Sorry, the content in 4000. Yeah, so the next question is related to figuring out the accumulator content after the execution of this following instruction. Okay, so let me write what does each instruction do. So MVIA means move this content, move 55H to A. Okay, then we have something called as RLC. So RLC instruction is, so this is my accumulator and this is the 7th bit and this is my carry flag. Okay, so RLC, it means rotate accumulator left.
B.
Okay, option, okay, so we got one answer. Let's see. So rotate accumulator left, so it means it will go like this, and then what happens is it will go back here and this bit will go to carry. Okay, so in the first step we will do it step by step. 1 2 3 4. In first step the content of accumulator is 55. So 55 is 0 0
0 1.
sorry 0 1 0 1
0 1.
Similarly,
Again 0 1 0 1.
0 1. This is in step 1. In step 2 what happens? RLC, so it should move one bit to the left.
Left. Yeah.
Yeah.
1 0 1 0 1
Correct.
0 1 0.
This is 1 0 1 0 1 0 1 0. Similarly, for the next step,
0 1 0 1 0 1 0 1.
0 1 0 1. Okay. Then what happens in the last step?
1 0 1 0 1 0 1 0.
Okay. So the final state is A. So option B is correct. Okay. So in this question, so we could have stopped directly here itself. Okay, without even bothering. So not here, actually here. Okay, without even bothering about the other two instructions. So the reason is, so we see that the pattern 0 1 0 1 0 1 0 1 is actually a repeating pattern, right? So after the one that is present here, again comes the 0. Okay, and the second thing is the RLC instruction. So it is going to generate, if there is a repeating structure, the RLC instruction is going to generate that pattern after every count, every even count. Okay, but here what we observe is there is an odd number of count. So if the content is symmetric, Okay, then RLC even count, it will imply that whatever is the original value, you will arrive at that value. If it is having an odd count, then perform RLC only once. Okay, so let us say there would have been 6 more RLC statements. Okay, then also the result would have been same, that is AAH. Okay, is this clear?
Yeah.
Okay. Does anyone have any doubt in this question? Okay, we can move to the next question then. Okay, so in this question, so we have to identify, so after this particular instruction is executed, so what are the contents of this BC register pair?
See.
Sorry, did anyone give an answer or something?
Option C.
Yeah, okay. Yes, option C is correct. So LXI instruction is used for like 16-bit loading the 16-bit address into the register that is mentioned here. So in this case it is B, and what happens, the initial values, they are loaded into B, and the remaining values, they are loaded into the next register, that is C. Okay, so this was question 11. The next is, okay, so the next question is also related to getting the accumulator content. Okay, so here we have used some more instruction, that is RRC. So RRC actually stands for rotate accumulator right. So bit 0 goes to bit 7 and carry. So this is analogous to RLC, the instruction that we saw before. Okay, but in this case what happens is accumulator is rotated to the right, okay, and bit 0, it goes to the carry bit. Okay, so next instruction we have RAL. So in RAL instruction, rotate accumulator through carry. Okay, let me call it RRC through carry. Bit 7 goes to carry and carry goes to bit 0. Okay, so RAL means rotate accumulator through carry to the left. Okay, and RAR means rotate, means to the right, basically the analogous of this one. Okay, so let us try solving this. So initially, okay, let me call this 1, 2, 3, 4, 5, 6, 7. Okay, first the content of A is F2. So F means 1, 1, 1, 1 and 2 means 0, 0, 1, 0. This is in first step. Okay, this is the content of accumulator. In the next step, what we need to do is, we need to do RRC. So RRC means what will be the content of accumulator. So it is going to rotate right, and in this case, okay, let me write the carry flag here. Initially the carry flag was 0. Okay, so what should be the content? Okay, what should be the content?
0 1 1 1
0 1 1 1
1 0 0 1.
1 0 0 1. Okay, this is the accumulator's content. In step 3, move B comma A. Okay, it means whatever content of accumulator we have, that will be moved to the register B. It means 0 1 1 1 1 0 0 1 is copied to register B. In fourth step, what happens? What should be the accumulator value and what should be the carry flag?
Accumulator value will be 1 1 1 1.
Accumulator
0 0
1 1 1 1. Okay,
0 0 1 0.
0 0 1 0. And what should be the carry?
0.
Okay. In the fifth step, what should happen?
Accumulator content will be 1 1 1 0 0 1 0 0 0 1 0 0 and carry will be 1.
Okay, carry will be 1. In the sixth step, what should happen?
A plus B.
Okay. Plus B is 0 1 1 1 1 0 0 1. So it should be 1 0 1 1. Is this correct? No. This should be 1. Okay.
Yeah.
Okay. So in the last step, what should happen?
The accumulator content will be 5T and carry is 1.
Accumulator content will be 5T.
5T.
It should be RAR, right?
Oh, last RAR, no?
Yeah.
Oh, sorry. Yeah, I have to do.
So can someone try the last? Okay, so here we have 1010, that is A. Then this is
Option A.
Yeah, option A is correct. Okay, so this is the final accumulator value that we will have, and the carry is still set to 1. So is everyone clear with the method that we used, or is there any doubt? Is there any portion that needs an additional explanation? Okay, so okay, let me once again just summarize this particular question. Okay, so what we did initially, we just moved the value F2 into the accumulator. In the second step, we did RRC. So RRC is the operation that is mentioned here. So the 0th bit, it will go to the carry. Initially the carry was 0. Okay, so 0th bit is again 0, so carry will stay at 0, but every other value moved to the right by 1 bit. Okay, so if I move to the right by 1 bit, then this one will come here, then there will be a 0 appended here, and the contents will move by 1 bit. So 0 1 1, and this one will go here, so it will be 1 0 0 1, and carry will stay at 0. In the third instruction, what we do is we move whatever content is available in A to a register called B. Okay, so this is basically a copy operation. We copied the content of A to B. In the next instruction, we do RAL. Okay, that is rotate accumulator through carry. It means carry will be involved and the accumulator has to be left shifted. Okay, so because we know the carry is 0, and if this is the value of carry, so what I do is I append a 0 here, that is supposed to be the carry value. Okay, and shift every other content to the left by 1 bit. So this is what we have done in step number 4. Step number 5 is again a repetition, but in this case what will happen is, because this bit is 1, it will go to the carry, so the carry becomes 1, and then left shift every other thing. Okay, then you obtain the value that we obtained in the step number 5. Okay, in step number 6, whatever value we stored in the register B, we add that value to accumulator, so the accumulator becomes 0101 1101 and the carry is 1. In the final step, what we do is we perform RAR, that is analogous to RAL, but in this case, instead of moving to the left, we shift the accumulator content to the right. Okay, so finally we obtain 1010 1110 as the answer. So 1010 is A and 1110 is E. So our answer is AEH. Okay. Okay. So the next question is, what is the size of program counter in 8085 microprocessor?
16 bit.
Correct.
16 bit.
Yeah. Which of the following register is not a general purpose register? B, C, D, or
A.
A.
Yeah. So A is basically an accumulator. So B, C, D are the general purpose register that is available in 8085 microprocessor. Sorry. So which of the following flag is not available in 8085 microprocessor?
Overflow flag.
Overflow.
Correct. Okay, sign flag is available. It denotes if it is 1, then the accumulator content is negative. 0 flag is available, carry flag is available, but overflow flag, it is not available in 8085 microprocessor. Okay, so these were all the questions that I planned for today's session. I'll give a summary of whatever we covered in today's session. Okay, so we started the session from T states. So T states is basically an unit that we use to define what is the delay that is being taken by an instruction to execute. Okay, that is basically 1 by frequency of operation of the microprocessor. Okay, and for move instruction it takes 4 T states. So if 1 by f clock is the time taken for 1 T state, then for 4 T states it will be 4 by f clock, right? So similarly, I just mentioned some few more instruction along with their T states. These are some commonly used instruction. MVI will take 7, move will take 4, JNZ will take 10 T states in each execution, except the last. The terminal state is going to take 70. So please remember this. The ORA instruction will take 4 T states, LXI instruction will take 10 T, DCR will take 4 T states. Okay. The next question was related to stack pointer. What happens to the stack pointer after push instruction is executed? And these are the few important points that should be noted down. That stack pointer, it grows backwards, and push and pop are the 2 instructions that are used for stack operation. Push is used to store content into the stack, whereas pop is used to retrieve the content back from the stack. And the behavior of the stack is last in first out. Okay, so whatever is entered last into the stack, that will be the first thing after the pop operation to be expelled from the stack. Okay, so similarly then I mentioned an example of push B. So if push B is done, so the first thing that will happen is, because the that stack grows backwards, so the stack pointer will decrement. Okay, next thing is, whatever content is present in B, it will be copied to the memory location that is being pointed by the stack pointer. Next thing is, the stack pointer will again be decremented, because push B means both B and C contents are going to be pushed into the stack pointer. Okay, so the stack pointer is decremented again, and whatever is the content of register C, it is copied into the location pointed by stack pointer. So overall there are two decrements in this process. Yeah, so the content of the stack pointer is decremented by 2. Okay, then next question was related to the updating of the program counter. So program counter updates each time to carry the new instruction that is going to be executed, and out of these options, all the instructions is the correct answer. The next question was related to the memory range that is going to be used, and here we observed what is the use of a chip select signal. So let's say you have multiple chips available with you, multiple memory chips. So chip select will be used to enable any one of them. Okay, so using this chip select signal, so what we do is, we first figure out at what value will the chip select be high. Okay, so CS is equal to this particular combination, so it is going to be high when A15, A14, A13 assumes the value 110. Okay, then the remaining bits can occupy any value. From there we figured out what is the least value that is possible, that is 1100, and rest all 0, right? And the highest bit, what is the highest value that can be achieved, so that was DFFFH, right? So this is 1101 and rest all are 1. Okay, so that is the maximum range. So C000 to CFFF and D000 to DFFF. So that is the complete range of the memory. Okay, so the next question was related to the contents of accumulator and the status of the carry flag and sign flag. So we perform the sub B instruction. So sub B will basically it'll do A minus B. That's what we did. Whatever content was present in A, we subtracted it from minus B, and we observed that the accumulator value is F1, and the carry is equal to 1 indicates that there is a carry from the last bit. Sign is equal to 1 indicates that the number is a negative number, right? The next question is a kind of continuation of question 1. So in question 1 we tried to figure out what was the, no, we did not figure out. In question 1 we did what is the number of t states that is required, but as I mentioned that t state is equal to 1 by f clock. So from there, using that total time taken, this equation, you can figure out what is the number of t states if the total time required for instruction execution is given to you. Okay, so the next question was, you have a set of instructions that is given to you, and you have to figure out what is the accumulator content finally. Okay, so that's what we did. First we moved the value A, the value 65 into accumulator, then the accumulator is added with the value B, so that becomes 77H. Next we complement the accumulator, and after complementing we perform the AND immediate with 68H, and we end up with 08H as the answer. Okay, next question was related to calculating the total loop delay that is produced by this given program, and so here we first calculate what is the loop delay outside the loop. Next, we figure out what is the total loop delay inside the loop. So for figuring out what is the total loop delay inside the loop, we need to figure out how many times the loop is going to be executed, right? And we saw that the total times the loop will be executed dependent on the value of b, right? So BC register was containing 0123H, and I just converted it into decimal for easier calculation. So we observe that it is going to get executed 291 times, and so after figuring out how many times it will execute, we figured out what is the total delay associated with the loop itself. So you just sum everything up here, but the JNZ statement, it is going to take 70 states instead of 10. So what we do is, in the last iteration, we just subtract -3. Okay, if we subtract -3, then it becomes 70 states. So total number of t states, we get 6981 t states for inside the loop operation. For outside the loop, it was 10t. So total delay associated with this instruction is 6991t. The 8085 was operated with 5 megahertz clock, so 6991 by 5 microsecond is the total time taken. That becomes 1.398 milliseconds. Okay. Then what we did is, so this question was related to the addressing modes that is available in 8085. LDAX B is a form of indirect address mode. Next is, so this is also related to the content of the accumulator, but here we use RLC instruction to figure out what is the final content of the accumulator. Okay. And here we observed another thing: if the accumulator content is symmetrical and if we are executing RLC, so if the total number of RLC execution is even, then the initial content of accumulator is the final content of the accumulator. If the total number of RLC instruction is odd, then we need to perform the RLC instruction only once. So even if the RLC instruction is given to us 17 times, so we know that it is the content of the accumulator will be same if the RLC is executed only once, right? So this is a trick you can use to solve bigger problems, only if you observe that the content is symmetric. Okay, so the next question was related to the contents of BC pair register using the LXI B instruction, and that is going to be, so B will be having AB and C will have CD. The next question was also related to figuring out the content of the accumulator after the execution of this particular set. So in this question, the in instruction like RAL and RAR, the carry also plays a role, because whatever is the carry flag that moves into the accumulator. So here you should be a bit cautious while solving these questions, because many a times whenever this rotate instructions are used, so people tend to forget that whether carry has to be included or not. So please at least remember this, that where carry is included, where carry is not included. Next question was related to size of the program counter in 8085 microprocessor, that is 16 bits. So accumulator is not a general purpose register, so option D is correct. And out of this, so only the overflow flag is not available in 8085 microprocessor. Rest all the flags that are mentioned, that is present. Okay. So if anyone has any question related to whatever was covered in today's session, then please let me know, or else we can wrap up today's session. So that's the end of today's session. So if anyone has any question, then please feel free to ask. Thanks everyone for joining. So please let me know if you have any queries that or Thanks for joining. Yeah, so regarding this session, if anyone still has any queries after the session is over, then you can post your queries on the forum. Recording of these sessions will be available on the YouTube channel. This session as well as the remaining sessions, everything, the recordings are available already on. For this session, I'll upload the recording after 5, but for the previous sessions, it is already available, and the slides will also be updated, and I'll upload them. So using the Excel sheet, you can visit the slides as well. So yeah. So I'll still be present here. Please let me know if you have any queries that you feel you want to discuss. Okay. YouTube link for previous classes. Yeah, sure. I'll share it. So this is the link for my YouTube channel. So there you can go through the previous sessions that was covered. And the slides are also uploaded, so in the Google Drive link. So in the Excel sheet, I think it will be mentioned, that is shared by the NPTEL team. So it will be mentioned that these are the slides. So the annotated slides will be mentioned. And yeah, the best thing, the best possible way in which you can revise these questions is not looking directly at the answers, but trying to solve the questions on your own, and see where you are stuck, or if you are not arriving at the correct answer, then only you go back to the solution. But initially you should give it a try after going through the lecture that is covered in the class. Okay. So I hope these tutorial sessions will be helpful for solving your assignment problems later and even for the exam. Okay, if anyone has any queries, then let me know. I'm still available here. Just let me know if you have a question. Okay. Thanks everyone for joining. If anyone has a question, then please let me know. Hello. Hi Satya, do you want me to go through whatever questions we have covered today? Okay, let me go through the questions that we covered today. So, the first question was related to getting the number of states required for execution of move A comma C. Okay, and then I listed a few instructions, the commonly used instructions and their T states. And basically one T state, so T state is kind of a unit that we use to measure how much time an instruction is going to take. And so one T state is actually 1 by frequency of operation of a microprocessor. Okay, similarly 4 T state will imply 4 by F clock, that is the operation of frequency of operation of microprocessor. Second question was related to the push instruction. So push and pop are the two instruction that is used for stack operations, and stack is usually a memory, it's a memory location, and it grows backwards. So when I do a push instruction, the first thing that happens is it decrements the stack pointer. Stack pointer points to the memory location from where the stack begins. Okay, and push B will imply that I have to push both B and C's content into the stack. Okay, so initially the stack will decrement once to push the content of B, then the stack will decrement second time to push the content of C into the stack memory. So there are two decrements, and there is a decrement because stack grows backwards. Okay, the next question was related to the program counter update part. So the program counter, it holds the next instruction that needs to be executed. So the answer to this question is all instructions. The next question was related to the memory range of this particular thing. So here chip select, the equation for chip select is given, and chip select is a signal used to select out of a given set of chips. If you want to select any one chip, then you have to figure out for what value of A15, A14, A13 that chip select will be 1. For this case it is 110, because A15, A14, A13 bar gives you chip select is equal to 1. After we figure out what is A15, A14, A13, the rest of the bits are free to use. So I have given XXX there. Okay, so the lowest value that it can occupy is C000, the highest value that it can occupy is DFFF. Okay, based on that, option C is correct. Next question was related to the contents of accumulator, and so this is a subtraction operation, so in which A minus B is performed and the result is stored in accumulator. So from the operation that we have done here, we can observe that F1 is the result that is stored in the accumulator, and because the obtained result is negative, so the sign flag becomes 1, and because we have a carry out here, so the carry flag is 1. Next question was related to figuring out the number of T states needed for execution of instruction. The total time taken for a microprocessor to execute an instruction is the number of T states into 1 by f clock. Okay, so using this equation you can figure out what is the total number of states. You already know what is the total time taken, that is 1.6 microsecond. You know f clock, that is 5 megahertz. So you just need to rearrange and figure out the number of T states, that comes 8. Okay, so the next question was related to the content of accumulator. Okay, and so here step by step we have done. First thing we have done is A contains 65H, then the content of accumulator is modified here at add B location. Whatever is the B's value, it gets added to the accumulator and accumulator becomes 77H. Then for CMA instruction, we complement the content of accumulator. ANI, we AND the accumulator content with 68H. Okay, so 08H was the answer. For the next question, we had to figure out what is the total delay that was being produced by this program. The first thing we observed is there is a loop. So whenever there is a loop, you figure out what is the delay associated inside the loop, how many times the loop is going to get executed. Okay, and you first figure out the total loop delay. So total loop delay in our case was 6981 T states. Okay, there is a minus subtraction here. It's because the J and Z statement, it takes 10 T states for each execution, but the terminal execution is of 7 T states. Okay, so to account for the terminal execution of 7 T states, what I have done is at the end I have subtracted -3. Okay, so we arrive at the total loop delay as 6981 T states. The the delay outside the loop was 10T because only one statement is outside the loop. So the total delay associated is 6991 T states. Okay, and from T states we can convert it into microseconds or the time units by using this information that it is a 5 megahertz clock. So 6991 by 5 megahertz will give you the total time taken as 1.398 milliseconds. Next question was related to the addressing mode. So LDAX-B is an indirect addressing mode. Next question was related to the content of accumulator after execution of RLC statement. So RLC is basically rotate left. Okay, and we obtain AAH as the answer to this question. Next question was to figure out the content of BC register. Okay, so the content of BC register is AB and CD for C. Okay, the 12th question was related to again figuring out what is the accumulator content after the execution of all these programs, and so RRC was so RAL and RAR are rotation along with the carry, so it is called as rotate accumulator through carry. So if it is L, it means rotate through left. If it is R, it means rotate to the right. Okay, but these operations include the carry flag as well, so you need to be careful while performing that. And using these series of steps, we figured out what is the content of accumulator as well as the carry flag, and the final answer that we obtained is AEH. Okay. Next is the size of program counter, that is 16-bit for 8085. Then A is not a general purpose register, that is accumulator. Overflow flag is not present in 8085 microprocessor. Okay. So these were the problems that we did. If you want to go through the complete session from the very beginning, so the recording of the session will be uploaded in the YouTube channel. So after an hour or so, you can give it a look. If you have any queries that is related to today's session, you can post it on the NPTEL forum. if you have any queries in this session itself, you can let me know. Okay. So if you have any query, then you can unmute yourself and let me know. Okay, I'll still be present here. Just let me know if you have a query. You can type it on the chat box or you can unmute and ask your query here.